Okay, this is covalent bonding in the periodic table. We've talked a little bit about ionic bonding, where valence electrons are transferred. In covalent bonding, valence electrons are going to be shared. And we think about this in our octet rule of elements doing everything they can to get 8 electrons in their outer shell. Nonmetals behave a little bit differently. Just as a reminder, we've got the stair step on the periodic table where we have metals on the far left-hand side, and we have nonmetals in this little section on the right-hand side. So if we have some elements bonded together on this right-hand side, to the right of the stair steps, we immediately think that they are covalently bonded. So we're going to start with fluorine, which is actually bonded to itself. Fluorine is an F2 molecule. So F2 means we have one fluorine and then another fluorine. So we have fluorine on our periodic table with its 9 protons, and it's in group 17, so it's got 7 valence electrons. So if I were to draw the picture for it, I have 9 protons. First level, 2 inner electrons. Second level, 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Notice fluorine is 1 away from accomplishing its goal of getting 8 valence electrons. There's another fluorine right next door to it with its first level having 2 inner ones, and its second level having 7 outermost ones. 1, 2, 3, 4, 5, 6, a little disorganized, but that's okay, 7. These fluorines know they're bonded. They look at each other and say, well, I've got 7, so I'm not going to give you one of mine, because I don't only have 6, I'm trying to get to 8, and this fluorine says the same thing. So what ends up happening is the fluorines actually share an electron, and the electron they are a pair of electrons. So the pair of electrons they're sharing are right here. So now in theory, in terms of valence electrons, this fluorine over here has 1, 2, 3, 4, 5, 6, and is sharing these 2 to make 7 and 8. And over here, this fluorine also has 1, 2, 3, 4, 5, 6, and is sharing these 2 to make 7 and 8. So both these fluorines have found a way to satisfy their octet rule, which is the attempt to get 8 valence electrons, by sharing a valence electron. In symbols, we represent this like this. We say one fluorine is single bonded to another fluorine. We'll work more with that at a different level. We could also do something similar with oxygen. We go to our periodic table. Oxygen is to the immediate left of fluorine. It's in group 16, so oxygen has 6 valence electrons. Okay, oxygen's formula is also O2, which represents one oxygen bonded to another. So here we go with one oxygen with its 8 protons, another oxygen with its 8 protons. First level, 2 inner level electrons. Second level, 6 valence electrons. 1, 2, 3, 4, 5, 6. Over here, the same thing. First level, 2.
Good morning.
Morning. Second level.
Oh my God.
1, 2, 3, 4, 5, 6 valence electrons, and these oxygens look at each other and say, hey, we're supposed to be bonded. But I've got 6, I'm not going to steal 2 from you, leaving you with 4, and both these oxygens are in the same position, so their octets are, their valence shells are nearly full. They just both have to find a way to get 2 more electrons in that outer shell. So like fluorine shared this pair of electrons, oxygen is going to go ahead and share 2 pairs of electrons. So now in terms of valence electrons, this oxygen feels like it has 1, 2, 3, 4, 5, 6, 7, 8, as well as this oxygen feels like it has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. And that's represented in symbols, kind of like this, with O double bonded to another O. A lot of times too, the notation calls for these other valence electrons to be represented. So these 2 red ones here can be represented right here, 1, 2. These 2 here can be represented down here, 1, 2. Color doesn't matter. And then these 4 electrons over here, this pair here, and this pair here. Ultimately, we get kind of creative with this theory. A very common molecule that we deal with is carbon dioxide. And we'll kind of show how that works in terms of its valence electrons. Carbon dioxide is CO2. Okay, we're going to arbitrarily put carbon in the middle. Carbon has 6 protons, oxygen has 8, and just kind of watch how it works here. So carbon with its 6 protons. First shell, again, it has 2. Second shell, to get to 6, it's going to have 4. So 4 valence electrons. I'm going to spread them out here, 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 and here. Oxygens, I'm going to draw the same thing I did earlier on both sides. So 8 P pluses. First level with 2 inner electrons. And second level with 6 valence electrons. 1, 2, 3, 4, 5, 6. I'm going to do the same thing over here. 8 protons. First level. Second level. First level, 2 inner electrons. Second level, 6. 1, 2, 3, 4, 5, 6. And now these molecules know they've made carbon dioxide. They look around, they've got to find a way to satisfy their octet rules. So carbon is also a nonmetal, so it doesn't want to give away electrons. Okay, it needs 4 more, and the oxygens, as we described earlier, need 2 more. So here's how they find a way. The carbon says, okay, oxygen, I'm going to share with you here and here. And I'm going to do the same thing over here. So we're going to share here and here. So now in terms of octet rules and valence, having the idea of 8 valence electrons, this oxygen, 1, 2, 3, 4, 5, 6, and 2 more to make 7, 8, feels like it's got a complete octet. This oxygen over here, same thing, 1, 2, 3, 4, 5, 6, 2 more to make 7, 8, has its octet rule satisfied. The carbon in the middle has 1, 2, 3, 4, and is also sharing 5th, 6th, 7th, and 8th electrons. So in that fashion, through covalent bonding, all 3 atoms have achieved that octet rule with 8 valence electrons. In terms of symbols, which we'll work on a little bit later, this looks kind of like this. C double bonded to O this way, and C double bonded to O this way. We can also represent the other 4 electrons on each oxygen, kind of like this. But ultimately, we think back to ionic bonding, where electrons are transferred between a metal and a nonmetal, and covalent bonding, where electrons are shared between two nonmetals. Remember, if we see two things bonded on the right-hand side of the periodic table, we want to think electrons being shared, as opposed to earlier when we learned that if we had a metal with a nonmetal, kind of like NaCl, that electrons were transferred.